So we're going to cover section 12.1 here, which is analysis of variance. And I want to start it out with a kind of a familiar data set, something that we dealt with before. If you go to the link that I sent you in the chat, then in the upper left-hand corner, there's a little drop-down menu. I'd like you to click that, and we're going to open up the roller coaster data set. So click the drop-down, open, and yes, it's okay. We can change things. Scroll all the way down to the bottom and open up the roller coasters data set. Now, if you can't keep up with this or you don't have the link or whatever, that's fine. It's nothing you're going to be crucial. But here we go. So kind of a fun data set. And we looked at this before when we were doing linear regressions. We're going to look at it again. Let's do a couple things. Let's take, first of all, the fun piece of data from this data set, which is your top speed. I'll do a couple things with it. You don't have to mimic the first one. You can hang loose for just a second. If I put the top speed on the x-axis, it's kind of nice. The dots self-organize themselves into something like this. Let me ask you a question about this. Does that look like a normal distribution? What do you think?
Yes, it looks relatively normal.
Yeah, it looks relatively normal. How could you test it if you're curious about it and you're like, you know, I think we should test it? What are some of the things you could do to test it?
You could copy and paste the data into StatDisk, but I don't know how well that will work.
All right, but in StatDisk, what would you do?
I'd go to analysis and then normality assessment.
Excellent.
And
perfect.
See what it says.
Yeah, so it gives you the Ryan-Joyner test. It gives you a box plot of the data. It gives you a normal quantile plot. So you can see a lot of things about the data. Now, I think the fun part with this data is when we have it on the y-axis and we have things that predict how fast you'll go. What's your maximum speed? Now, one of the things I was curious about, though, was this thing, which is the age group. Now, the age group is based on the year that these coasters were built. So before 1980, between 1980 and 1999, and after 1999, basically 2000 and on. So I'm going to drag that to the x-axis. And it's going to do something interesting here. It breaks it up into those three groups. So you still see the top speed, it's just now that you see it within each group. Now, I kind of suspected that there'd be a trend. I thought it would go from slower to faster, that the more recent coasters would be faster. Although there's quite a bit of variability here. Nonetheless, I still want to kind of cut through things and see some of that variability and see if there's really a difference between coasters built a long time ago and coasters built now. So another one of the cool things we could do is click the ruler here. Now the ruler gives us a lot of nice little options. What would you want to see on this graph to help you maybe understand it a little bit better? What sounds interesting? You get a lot of things you can choose from. Count, maybe percentage, mean. The mean? Yeah, okay, let's take a look at the mean. And the mean does look like it has a little bit of a trend. If you click on these bars, let's see, it's giving me the mean here. Mean here is 58.1 miles an hour. The mean here is 66. And the mean here is 49.4. So it looks like they're going up. Let's take a look at a couple other things. One of the things that's on your final exam supplement is the standard deviation. You should know what that is. Now, the standard deviation measures the spread of your data, how spread out from the mean it is. Which one of these standard deviations do you think would be the biggest? The older, the more recent one, or the newest one?
Newest one.
Yeah, the newest one. There's more spread from your data. Okay. fine. But what we're interested in overall is there a difference amongst these three groups? And that's a little bit of a problem here for us, because in chapter 9, we could test two different things, but now that we're looking at data that has three different groups, what do? How do you test a hypothesis with three means? Well, that's what analysis of variance does for you. And an ANOVA really is kind of like an acronym of sorts of analysis of variance. So it's kind of put together from these words, ANOVA. And what an ANOVA is for is testing hypothesis of this form. mu1 equals mu2 equals mu3. As many different means as you want, many different treatment groups. So this is always going to be the form of your null hypothesis, and your alternative hypothesis is going to be kind of this, it's called an omnibus alternative, like an everything alternative. At least one of the above means is different. Okay, makes sense. At least one of the above means is different. Okay, let me do a couple of problems by way of example, and then kind of get into the meat of the analysis of this. We'll do this in StatDisk. So let's look at a couple of problems on the handout that I sent you. The first one is just kind of a fill in the blank that you're going to see, probably one of the first problems you see in your homework, and that is a treatment is a characteristic of used in an ANOVA that allows us to distinguish different populations from one another. All right, nice. So in our case, the treatment for the roller coaster data is what age group it's in. Is it in the older, the more recent, or the most recent? So that would be the treatment. And for every analysis of variance, you're going to have a treatment variable, something that distinguishes your different groups. Now, again, some of your early questions in your homework here would be stuff like this. What characteristic of the data suggests to use an ANOVA? And you've got a bunch of choices. There are 3 samples of measurements. The measurements are categorized according to 1 characteristics of size, the population, means or approximately normal, or nothing specifically indicates that a one-way analysis of variance should be used. Well, I'll help you out. It's not that one. All right. Now, the population's means actually did look kind of normal, but that's not it at all. The thing about this that suggests that we do this as an analysis of variance is that the measurements are categorized to 1 characteristic, all right? And that characteristic, in this case, is size. In the case of our roller coaster data, the characteristic was, how old it was. So you're always going to be looking for those treatment characteristics, and analysis of variance is going to be used when you have typically 3 or more different treatments or different categories or different factors. You can use analysis variance for 2 different categories or factors, but then it kind of defaults into the stuff that we did in section 9.3. Yeah. All right. If the objective is to test a claim that the 3 size categories have the same mean chest acceleration, I guess I probably should have really taken the time to look at this data. It's data on deceleration of crash test dummies. So G is measured in the g-force of gravity for samples from small, mid-size, and large cars. So, okay. If the objective is to test a claim that the three size categories have the same mean chest deceleration, why is the method referred to as analysis of variance? So it's a good question. It's not something that I would expect you to necessarily divine without some help here. So let me just kind of jump to the happy ending real quick here. The method is based on the assumption that you have a common variance amongst all your data. And that common variance is used as part of the analysis to try and figure out, okay, well, if there is this common variance, then, you know, what's happening within each group. Now, to better understand that, let's take a look at the analysis of variance table itself, how you set things up. So you should have this handout. Talks about an analysis of variance test. Here's your null hypothesis that you have these K treatments or factors that distinguish your groups. And what you do is try and measure some sources of variation. There's two different possible sources. There's an error source of variation, and there's a treatment source of variation. So part of the differences you see in your data are due to the treatment, and the other is just error. Now, if a lot of the differences that you're seeing between the treatments account for a lot of your variation, then this total is going to be high. It's called SST, sum of squares treatment, and then here you have sum of squares error. But if this one is really high, then when you form some subsequent ratios, you get the mean square for treatment is really this total divided by its degrees of freedom. And then the sum of squares error divided by its degrees of freedom gives you the mean square. These two are taken into a ratio that gives us an F test. If the mean squares for treatment is much bigger than the mean squares for error, then this is going to be a really big number, and you're going to get a significant test. The bottom line that we need to understand is that large values of F from the F distribution suggest that there's a significant test and that you're going to be rejecting the null hypothesis. By the way, there is a little bit of a typo here. You should probably fix that up. This should be H sub 1 or H sub A, depending if you like one notation or the other. Anyways, you're going to reject H naught if the F test is large. Now, how do we determine that? How do we determine if it's large? Well, with our significance level alpha, if the p-value is greater than, or p-value is less than alpha, then you're going to reject. If the p-value is greater than alpha, you'll fail to reject. Just that simple. The rest of it is just like our usual hypothesis test. Let's do kind of one more warm-up example on this stuff. In a test of weight loss programs, 200 subjects were divided such that 40 subjects followed each of 5 diets. Each was weighed a year after starting the diet, and the results are in the Anova table below. Use a 5% significance level to test a claim that the mean weight loss is the same for the different diets. So you've got some measure down here that measures how much variability there is in the data. Some of that variability is within groups, some of it is between groups. Those two things have degrees of freedom associated with them. That's what you get. That's what you use to get your mean square for treatment, mean squares for error. For this top one, you're going to take the 532 divided by 4. That'll give you this, the 133. For the bottom one here, the sum of squares for error, or sum of squares within groups, take this number divided by 195, and that gives you this. It's the ratio of these two that give you your F statistic. Now, all that's great. And in a face-to-face class, I'd probably ask you to know a little bit more about how this is done. But there's really only one thing that we need, and that is the p-value. Later today, I hope to discuss with you a little bit more about why the p-value is what it is and how it works. But for right now, we've got a p-value. What does that p-value tell us about the null hypothesis? Are we going to reject or fail to reject?
Reject.
Yeah, reject. The p-value is less than alpha. If alpha was 1%, would we reject at that point? Anyone? If alpha was 1%, 0.01.
You would still have to reject it.
Yes, we'd still reject. Good. Yep. So you got a pretty small p-value, so you're going to be rejecting at our typical values of alpha. So should the null hypothesis that tell that all diets have the same mean weight loss be rejected? And the answer is yes, because the p-value is less than significance level. Yay. Okay, so you're going to reject that mu1 equals mu2 equals mu5, et cetera, in favor of the alternative that at least one of them is different. And that's as far as you can go with it. At least as far as we're going to go with it in this class. There are other things you can do to kind of follow up with that and say, all right, well, it's this mean that's different than the others, et cetera. Now, a little confession here. A lot of the things that we've done in this course, you can do on a graphing calculator. And this output here is actually from a graphing calculator. It's just the problem with graphing calculators is getting the data into the graphing calculator. It's just not that easy. I can't put data in the chat and send it to you and have it appear on your graphing calculator. The day that happens, I might start using the graphing calculator a little bit more. But I think there's too much good technology out there to waste time on a graphing calculator. Let's look at example C. Samples of pages were randomly selected from 3 different novels. The Fleisch reading ease scores were obtained from each page. And the TI-84 plus calculator results from analysis variance are given below. Use a 1% significance level to test the claim that the 3 books have the same mean Fleisch reading ease score. What's your conclusion about this? What is the conclusion for this hypothesis test? Well, let's actually run through this as a regular hypothesis test. So the first thing is to state our null hypothesis, right? So step 1, H0. Your null hypothesis always has this form. mu1 equals mu2 equals mu3. So for these 3 books, their mean Fleisch reading E scores are all the same. The alternative, as it is for all these, is at least one of the above means is different. Okay. What's our typical step 2? What do we usually use for step 2?
Determine alpha.
Determine alpha. So they mention anything about alpha for us here? Yes, they do. Alpha is 1%. Step 3 for us is typically put in the data. That's already been done for us. So that brings us down to step 4. What's our typical step 4? What do we usually get from step 4?
P-value.
The p-value. Good. And what's the p-value for us this time?
6.9194.
6.9194. Okay, cool. You gave me an extra digit than even I put, so wonderfully accurate there. Although it kind of doesn't make sense for the moment because p-values are probabilities. Since we're getting close to the final exam, let me remind you of something. Probabilities are between what and what values?
0 and 1.
0 and 1. So a p-value of this magnitude doesn't seem to make sense. But if you look back at our output here, there's a little bit something else going on here. And that little extra something there I highlighted in blue, it's E -4. Now I'll have to help you out with something here from the TI graphing calculators. This is really your calculator's shorthand notation for times 10 to the -4th. It's basically putting it in scientific notation. And if it's times 10 to the -4th, if I put it back in decimal notation, I have to move the decimal 4 places to the left. Once I move it here, the rest are going to get filled in by 0. So I'll have 3 zeros. And then my 69194. That looks like a p-value. That's a number between 0 and 1. So good. Good deal there. That brings us to step 5. Are you going to reject or fail to reject?
Reject.
Reject.
Good. Thank you, ladies. Reject H0. And then step 6 is to state our claim and state our conclusion in words. Let's look back at the original wording this. Test a claim that the 3 books have the same mean Fleisch reading score. So basically the way I see it is you're answering yes to this question. Does the original claim contain the condition of equality? Yes. Did we reject it? Yes. So there is sufficient evidence to warrant rejection of the claim that the 3 books have the same mean Fleisch reading score. And I apologize if I'm pronouncing that wrong. There is sufficient evidence to warrant rejection of the claim that the 3 books have the same Fleisch reading score. Rejection of the claim that the 3 books have the same Fleisch reading ease score. Yeah. How's that one looking? Doing okay for example C on this stuff?
Yep.
Awesome. Awesome. Okay, let's move on to example D. And let's do that here. 12.1, example D. So the data below measures the amount of greenhouse gas emissions from 3 types of vehicles. The measurements are in tons per year expressed as CO2 equivalents. Use a 0.025 significance level to test a claim that the different types of vehicles have the same mean amount of greenhouse gas emissions. Based on the results, does the type of vehicle appear to affect the amount of greenhouse gas emissions? All right, so finally we get some data to work on. Let me see if I can't grab that data for you and post it in the chat. It'd help if I grab all the data. And we'll put this into stat disk. So the data looks like it made it into the chat. And hopefully you can get that pasted into stat disk. Actually, I guess I got to open that up myself. Okay. In fact, I think they've got it already pasted in here. So I'll give you a second to catch up to that. Let me go back to the problem here and look back at this. We're going to test a claim that the different types of vehicles have the same mean amount of greenhouse gas emissions. So step one for us has always been to state the null and alternative hypothesis. What's H naught going to look for us in this case? What's going to look like?
mu1 is equal to mu2.
How many groups do we have?
Oh, can you go back, please?
Sure.
3. So mu1 is equal to mu2, which is equal to mu3.
Perfect. And the alternative, as always is the case, is at least one of the above means is different. Thanks, Laura. So that brings us to step two. Alpha was kind of weird in this one. Not what we typically get. Anyone catch what alpha was?
0.025.
Awesome, thank you, 0.025. So kind of odd on that one. Step three is to input the data. And step four, you're going to go to analysis. And let's take a look at where we're going to go after that. Maybe you can guess it, maybe you can't. I'm thinking you can. Analysis. Anyone see anything that looks promising here?
One-way
Analysis of variance.
analysis of variance.
Yeah, thank you both. One-way analysis of variance. So this one down here, and it's pretty simple. So just select the columns to include in the analysis. So it's going to be 1, 2, and 3 for us. Now, a quick word here. There's not much in the way of assumptions here that I'm going to fuss you about. Trying to think, should we look back at creating the Anova table? Yeah, I mean, mostly that the standard deviation is the same for all our different groups. So let's take a look at the analysis then.
Don't you have to change your significance level?
Oh, I should. Yeah, that'll change the plot. It won't change the analysis though.
Okay.
So when I run this again, I get the same numbers, but you're right, I should change that. So step 5. Actually, for step 4, what should I write down for step 4? I've got this nice, neat little list of things that we're working on, but I actually didn't write down the important thing for step 4 that I need to. What should I write down for step 4 here?
The p-value.
And the p-value was shooting blanks, 0. Awesome, thank you. So the p-value was 0. What's it telling us about our null unalternative hypothesis?
Reject null hypothesis.
Yeah, thanks, Rosin. Reject H naught. Yeah, basically our p-value is less than alpha. So wonderful. The wording, the conclusion here is the same as it was just a minute ago. And that is, there's sufficient evidence to reject the claim. Remember our original claim, I like to call it the orange claim, and I always circle it in orange. The original claim was one of which contained equality. So we can use that wording and conclusion thing to follow the same path that we did before with example C. There is sufficient evidence to warrant rejection of the claim that the greenhouse gas emissions are all the same. Could probably be a little bit more careful than that. Okay. How's that one look? Are we getting a little bit more comfortable with these things? Now, like I said, it's some subsequent analysis that allows you to do something more than conclude this, that at least one of them is different. I mean, sometimes the data might be just jumping out and saying, yeah, okay, one of them's different, but which one's different? How is it different? What's the confidence interval for mu in that sample versus mu in this sample, et cetera? So there is a lot more work that you can do here. We're just kind of limited by the fact that this is a first semester course and we just don't have time to cover everything. It's a whole world more of statistics out there that we could work with. But this is a great start. Okay. Nothing more on that one? All right. So let's move to example E, which talks about the milligrams of nicotine in different cigarettes, different king size cigarettes, 100 millimeter menthol cigarettes and 100 millimeter non-menthol cigarettes. The king cigarettes are non-filtered, while the 100 millimeter menthol cigarettes and the 100 millimeter non-menthol cigarettes are filtered. Use a 5% significance level to test a claim that the 3 categories of cigarettes yield the same mean amount of nicotine. All right, well, so once again, I've got to paste some data for you. So let me grab that out of our tables here and dump that into the chat. It didn't go through the way I wanted to. Let me, uh-oh. No, I didn't mean to, I quit my program, rats. Let me see if I can't get that data in a format that might stick. Let's see. Sometimes if I copy it from Excel, it works a little bit better. All right, I think that one worked a little bit better. At least I hope it did. Someone let me know if that came through okay. Be able to paste that into StatDisk.
It worked for me.
Okay, that's good. So if it works for one, it works for all? Is that the way it works? All right,
For
I hope
me.
so. Good deal, good deal. Okay, so we've got that pasted in. And I'm going to just paste mine into these three columns here. So when I run my analysis of variance, I'll just have to select different columns than you do. But let's do this just like any hypothesis test. Step one is your null and alternative hypothesis. So step one. Somebody I haven't heard from yet today. What's HO going to look like?
mu1 equals mu2 equals mu3 and so on.
Perfect. And the alternative is that at least one of the above means is different. Now, if we want to make this our last example, then I need you to show me that you understand what's going on. So guide me through what's next.
Significance level.
All right. What are we going to use for the significance level here?
0.05.
Awesome. 0.05. Thank you, Jada. Thank you, Laura. Step three. What's step three basically for us? What do we do in step three?
Input the data in StatDisk and then
Input the data.
analysis.
Good. And that takes us to step four, which we haven't done yet. So let's go over to StatDisk. StatDisk, analysis, one-way analysis of variance. Got this set up. Now, I don't know about you, but for me, my data is in columns 4, 5, and 6. If you just cleared things out and pasted it in, your data might be in columns 1, 2, and 3. Not sure. Evaluate, and here's what you get. What do I need here for step 4? Someone I haven't heard from yet.
You need the
P-value.
P-value, wonderful. Several voices on that, and the p-value is 0.03667. Awesome.
and it asks for the F statistic as well on this problem. So I don't know.
So let's see. What's the F statistic?
Is it
What do you think?
74556?
Yep. 3.74556. Although they might have you round that to a specific amount. Now, the actual F statistic gives you a different way to test things than we've done with our p-values. So based on the p-value, let's take a quick look back. What's going to be our decision in step 5 based on the p-value?
Reject HO.
Excellent. Thank you, Carly. Reject HO because the p-value is less than alpha. Now, to kind of understand that, and I'm going to go over this more later today, But what's going on is this, the critical value of F is right at the point that would mark a p-value of 0.05. And what that means is that if the null hypothesis is true, there's only a 5% chance of getting an F statistic this far out in the right tail. And guess what? We got something further to the right than that. So the p-value for this is even less than 0.05. So what we feel is that it's unlikely that we could get this data and have an H naught that's true. So it could be unlikely. It could happen. So we could be making a type 1 error and rejecting H naught. But the probability is against that. There's only like a 3.74% chance that we're making a type 1 error. So this is the way I used to do these hypothesis tests, as I set up the fail to reject region, which is to the left of F, the reject region, which is to the right of this red line for F. And if your test statistic fell to the right or to the left, that's how you make your decision. I think it's easier, it's a better way to work on this overall, to work with the p-value. Because the p-value lets the user or the reader of your data make their own decision. They might say, hey, you know what, I always deal with alpha is 0.01. Would you reject at the 0.01 level? If alpha was 0.01, would we be rejecting H naught?
No.
No. So by giving somebody the p-value, you're giving them the means to make their own decision, which is great. You're not forcing a decision on them. But in our case, we're going to go with p-value of 0.05. So that means reject. And now it's state your conclusion in words. There is sufficient evidence to warrant rejection of the claim that all the cigarettes have the same mean content of nicotine. Beautiful. How are you looking with analysis of variance? You comfortable with that one?
Yep.
Awesome. Awesome. Thank you. Any questions on analysis of variance? It's a really cool tool in your statistics toolbox that you can test for the equality of means across multiple populations. So, all right. So are we good? Do you want one more example from this section, or we all done? All right. I don't see any clamor for another one, so we'll stop things here. Good luck with this section.